A hollow cylinder and a solid cylinder have the same outer radius of 0.6 meters and mass of 4 kilograms. Same radius, same mass, and roll without slipping on a flat surface towards a ramp. Okay? All right, looked at problems 1 and 2 here, so we're going to go to 3 and 4. The initial angular momentum of the solid cylinder is, so this one right here, solid, L equals 9 kilogram meters. That's a lot of units. Okay? 9 kilograms meter squared radians per second as it rolls without slipping along the horizontal surface, which I know because it says without slipping, but still important. What is its kinetic energy? Okay, so there's 3 pieces of information we're given here. So the first one is without slipping. So that says that there's a relationship between the linear motion and the angular motion. We have x, the linear motion traveled, will equal theta, the angular distance traveled, times r. And this is intuitively makes sense because if you look at a circle, then the distance around the circle will be 2 pi r. That's the x. And then if you look at traveling around the circle, you'll travel 2 pi. When you multiply that by r, you get 2 pi r. So it's like, oh, okay, they kind of seem to match up. So that's why I usually write that one first, because it's intuitively makes sense. Then if you follow the same pattern, you have velocity equals angular velocity times radius. If acceleration is alpha, which is angular acceleration, times r. So that's what when you say without slipping, what's really being conveyed to you is these relationships are true. If there was slipping, it would not be true. Okay, we're also then told a angular momentum. So I always try and look at angular rotational kinematics in terms of or rotational motion as an analogy for linear. So this is momentum. So P equals mv. This is the linear momentum. And so angular momentum is L equals I omega, where omega is the angular velocity and I is the moment of inertia based on the geometry of the shape. Okay, yep, and so that's another piece of information. And then the other piece of information we're going to think about is total kinetic energy. So for total kinetic energy, we have energy kinetic equals 1/2 mv squared. This is the traditional translational kinetic energy. And then we're also going to have energy kinetic. I'm going to call this T for translational. This will be R for rotational. This is 1/2 I omega squared. The same analogy we had here where mass, we then write that as moment of inertia. And V we write as angular speed. Now, this isn't a rigorous derivation or anything like that. This is more of a mnemonic to kind of help memorize, okay, this is what's going on here. Okay, so now that we got these informations, we're given this, and we're asked to find that. So what we're going to do here is we're going to use the angular momentum to then find the speed. So we're going to I'm going to convert everything back into this translational relationship. I'm just more comfortable working with translational because that's why I learned first. It's more intuitive. Most people are that way. And so I'm going to take angular momentum. I'm going to use that to find the speed. And then the way I'm going to convert it is I'm going to use these relationships. And then I'm going to use that to convert it to the energy as required, because we're going to look for total kinetic energy. The first thing that I'm going to do is I'm going to write out what this total kinetic energy is. So this is our kinetic energy translational. This is our kinetic energy rotational. So our total kinetic energy is just the two of them added together. So we're going to start by writing 1/2 mv squared. Now this is the translational, moving sideways without rotating, plus 1/2 I omega squared. So this is our end game right here. So we start with the information that we're given. Whoop. Ooh, blue. L equals I omega. And we're told that this is the solid cylinder. So one thing that we know about solid cylinders, you can look up moment of inertia. You'll generally be given these, but there are a few you should have memorized. One of them is for a solid disk, which is the same as for a solid cylinder, because a cylinder is just a whole bunch of disks stacked on top of each other. And so the moment of inertia for that will be 1/2 mr squared. And I wrote r capital. You can write lowercase if you prefer. Not a big deal. So then this will be 1/2 mr squared. And now since we was rolling without slipping, we can convert this omega into the linear. So this one, come down here, omega equals v over r. That's supposed to be an r. So then we have v squared, nope, just normal v, v over r. Therefore, angular momentum will be 1/2, one of the r's cancels, mrv. And we know that equals 9 and then units of such. Okay, so now we got that done. And when we look at this, we're like, okay, we know what 9 is, that's just a number. We know what r is, that's a radius, we know what the mass is, and 1/2 is 1/2. So we can actually find out what the velocity here is. So here the velocity will be 9 times 2, because divided by 1/2, divided by m, divided by r. This is 18. Mass, I think, was 4, and radius is 0.6. So divided by 4 kilograms, divided by 0.6 radius. And I'm pretty confident I could do this in my head, but I am not going to. On clear, 18 divided by quantity, 4 times 0.6, unquantitied, we have 7.5. So we have, at this point right here, this solid cylinder moving at 7.5 meters per second. Okay? Seems reasonable? Yep, seems reasonable. I use into our equation up here, our energy kinetic total. So first thing I'm going to do is I'm going to rewrite it, 1/2 mv squared. This is the translational. Oh, that's terrible. Can't even read that. Plus 1/2. Now I here is going to be the same I that we had before. So 1/2 mr squared. So now we're looking at some sort of 1/4 value here. Mr squared. Yep. Terrible handwriting. It's okay. And then we're going to have omega squared. Now we know omega is angular velocity, which we saw earlier due to not slipping. It's going to be the same as v over r. But omega squared will be the same as v squared over r squared. Do some canceling, probably with a red. R squareds will cancel. We can rewrite this as, oh, sorry, this is the rotational energy. Rotational. 1/2 mv squared plus, these will become 1/4 mv squared. And we're left with 3/4 mv squared. So just intuitively look at this, you can think, okay, so 1/3 of the energy is stored in the rotating of the cylinder, and 2/3, no, yep, 2/3, because you break up 3 into, there is half as much energy in the spinning as there is in the translation. And that's just going to be for all cylinders that are rolling without slipping. Okay, so actually solving this, we have 3/4, mass is 4, and velocity is 7.5, but we're going to square that. The 4's will cancel, and we are left with a calculator. Square the answer, times 3. That's going to be a pretty big number. 168.75. 168.75, and this will be in joules. Okay? Look at our possible answers here. Yep, 169. So energy kinetic. I like to use EK sub K for kinetic energy, but other people use K. Totally reasonable, completely legitimate. So that's the way I kind of approach that problem. Start with using the momentum to find the velocity, use the velocity to then find the kinetic energy. And then I use the relationship of not slipping to kind of show that, all right, these things are related. All right, I'll erase this part. This part I'll leave here. Let me get rid of the arrow. Okay. So now for the next problem, number 4. If the two cylinders initially have the same angular momentum, about an axis through their center, and continue to roll without slipping up the ramp, which one goes further? My first thought is there's 2 different ways to approach this. First, we already know the kinetic energy of one of them. So if we do the exact same process we did last time, we could then get another total kinetic energy. Ooh, we could. I should have just left everything up there. Maybe that's what I'll do. So what I could do is I could assume, all right, they have the same angular momentum. We could be like, well, maybe that same number is 9. And then I could solve for how much energy the hoop has, or the loop, the hollow cylinder. And if that amount of energy is greater, then it goes further up the ramp. Or if it's less, it doesn't go as far. Actually, yes. That's exactly how I'm going to do this one. The more methodical way of doing it would be to basically write out what we did earlier, but instead of using 9 and solving for velocity, we just leave it as a generic term and then do more of a formal proof. I'm not going to do a formal proof. I'm going to say that this same angular momentum just happens to be 9. We're not proving it. So the idea here is we're assuming that it applies to all numbers, whatever the angular momentum has to be. So we're going to find one specific one and find if it's true. But you'll see. It'll be beautiful. Beautiful. Okay. So again, we're going to use momentum. So momentum equals mass times velocity. Angular momentum equals I times omega. We're then going to use that to find energy kinetic total, which is 1/2 mv squared plus 1/2 I omega squared. So we're going to use, so we know in this case, we're going to find it for the hollow cylinder, which is the same as a point. So if you have a point there, and you have like the axis rotation there, and the point's going like that, the moment of inertia for that, the I, will be mr squared. So that then that's going to be based solely on, if you take this dot and you basically smudge it all the way around in a circle, it's not actually going to change its moment of inertia. So one way to think about it is you have a dot, that's mr squared, and you have a hollow cylinder, that's just a whole bunch of dots arrayed in a circle of the same radius, which is then mr squared. So for a solid cylinder, moment of inertia was 1/2 mr squared. For a hollow cylinder, it's going to be mr squared, double what it is for the solid cylinder. And one way to kind of intuitively reason that makes sense is it's harder to rotate something that's further out. You think of it in terms of, yes, it should intuitively make sense to you. If something's hard out and you're trying to rotate it, it'll be hard. Think of it as swinging a long stick versus a smaller stick but of the same mass. The long stick will be harder to swing. And when you have the hollow cylinder, you have more of the mass towards the outside, therefore it's going to be harder to rotate. And that's what the moment of inertia is telling you, is how difficult it is to get it started rotating, to build up that inertia. Okay, so now that I've pseudo-justified that reasoning, you can accept that moment of inertia for a hollow cylinder, mr squared. So we have, let's see here, L, which I'm going to say we know is 9, equals I, which is mr squared. I'll go back to using capitals just because I enjoy it. And then V over R is omega. Oh, probably should make this capital. One of these cancels. And we're left with mrv. Before it was 1/2 mrv. Now it's just going to be mrv. Okay? So, yes. So V equals L over mr. Is that true? Yes, that's reasonably true. And we can find out what the velocity would be given the same sort of circumstances we had earlier. And we're assuming a 9 kilogram meters squared radians per second angular momentum. So calculator on clear. So we had 7.5 before. This time we'll have 9 divided by quantity, 4 times 0.6. We should get 3.75. Makes sense. Which is half of what it was before, 3.75 meters per second. So since they had the same angular momentum, this one is translating slower than the top one. Okay, so now we'll look at kinetic energy. Energy kinetic is do purple, show my evolution of thinking, 1/2 mv squared plus 1/2. This is going to be I, which will be mr squared times angular speed, which is v squared over r squared here, because there is no slipping. Cancel, cancel, and we are left with 2/2 of mv squared, so we'll have mv squared, which will be 4 times 3.75 squared. And go to the calculator. We have second enter squared times 4. We have 56.25. 56.25. This, I guess, will be joules. Before we had 169 joules. So this is the amount of kinetic energy it has. And so when that kinetic energy converts into potential, the higher initial kinetic energy will convert into more potential energy, i.e. further up, more height, extra h. And so, this one, the solid cylinder, will go higher up. And you might not feel intuitive why that is. It doesn't feel that way to me. But if we look back and kind of feel what happened here, what we're saying is, all right, these two shapes have the same angular momentum, meaning that they're both basically as spun up as the other one. Momentum generally relates to velocity, or in this case, angular momentum relates to angular velocity. And the more momentum you have, the more angular velocity you'll have too, generally. But with the moments of inertia kind of taken into account. Long story short, so this one, the solid cylinder, will spin faster because it has a lower moment of inertia. It's easier to spin. And since it's spinning faster in angular-wise, it's going to be, and not slipping, it's going to be moving faster translational-wise as well. And then if you're moving translationally, if your V is bigger, your speed is bigger, then that's going to have a bigger impact on your total kinetic energy, because kinetic energy is of the form 1/2 v squared. And so that difference, which is not as noticeable in momentum because it's only multiplied by a single velocity, single v to the first, that difference then gets exaggerated when you're looking at kinetic energy. I know, this is one of those times when you're almost better off, probably better off if you have time, to actually just go through the calculations and trust the math as opposed to trying reasoning it out. So the answer we got does make sense and it is reasonable, but it's one of those things, it's really hard to see why this is from an intuitive point of view. So this is about, maybe not the hardest kind of rotational problem you'll get, but from an intuitive point of view, this is fairly challenging. So I would not worry about life or focus too much on understanding this on a deep level. Just understanding that, all right, if I take this math and I throw it at it this way and jumble the box, an answer will come out that's probably correct as long as I don't make mistakes. I know, not reassuring, but that's kind of how these problems go. And that's kind of the approach that I would take for this sort of problem. So I hope that helped, and I will see you next time.